Swayam Prabha. Digital India. Educated India.
Okay. Again, mean, right? The measure of central tendency. What did we do with the probability, the discrete case? We said x times f of x, right? Take each value and multiply it by the likelihood of that value. Again, here you have infinite such values, but you can sweep through the density by integrating from the lowest possible value to the highest possible value, xf of x dx. Okay. Measure of dispersion, the same thing. Nothing is really changing except that the summations are getting replaced by integrals. But the math is going to be different, right? Because you have to either numerically or symbolically integrate. In the case of summations, you would actually take individual probabilities and sit and add it up. And that's very different in terms of how you implement something. But it's the same concept. You're taking each value x, now there are infinite such values. So you're going to each point, technically, looking at its deviation from mu, and asking yourself, what is the likelihood of seeing such a point that is characterized by the f of x dx? Okay? The same algebra that we saw, that we left for the tutorials during the discrete case applies here, where you can simplify this to a more convenient form, and you're going to repeatedly see this, right? In fact, so the mu square we discussed is called as expected value of x, correct? Now, what really is x square f of x? Right, so the answer is e of x square, but why is it e of x square in terms of, right? You take any function of x, and you're going to see this in a second. You take any function of x. So there is the PDF, which we're going to call f of x. But suppose you had some other function of x, g of x. This is not a PDF. This is just a transformation on x. Call it x square, call it 1 by x, call it ln x, whatever it is. Suppose you do g of x times f of x dot dx, integral from minus infinity to infinity. What you're getting is the expected value of g of x. You're basically substituting g, you're saying g of x, what is the average g of x to get? G of x, remember, is some transformation on x. It's like x cubed. So what is the average x cubed that I'm going to get? Take each possible value of x, substitute that value, get x cubed. I'm speaking of it in the discrete terms, but it's really in the continuous space. Substitute that value and multiply it by the likelihood of seeing that value of x. Now, this is a generalization, right? When g of x was equal to x, what did you get? Expected value of x, which is nothing but x f of x dx. So just an extension of that idea is g of x. So obviously now when you have x square f of x dx, it's nothing but e of x square, which is why often variance is written as e of x square minus e of x the whole square. So this is the whole square out here. Right? Again, we have not gone through the steps of simplifying from here to here. We'll leave that for later, because it's very simple algebra. You can take my word for it. Especially after all the linear algebra you've had in the last 2 days, it will be fairly elementary. Okay. So very quickly, let's just talk about two other fairly useful concepts, which are functions of random variables. So sometimes we are interested in a function of the random variable. We just spoke about. I mean, we used that a second ago by calling it g of x. But in the real world, sometimes you're not just happy characterizing this random variable. So I'll give you two simple examples. If the number of people who visit our store is a random variable, right? Let's say you're a shop owner. Let's say you're working for a major corporation, a mall. And the number of people who visit is a random variable. Now, your revenue that you make might be a function of the number of people who visit. More people visit, more revenue, fewer people. Now, let us say you had this mapping between number of people and the revenue you make. Now, what you have as a result, suppose you're interested in this random variable called revenue, right? that you can characterize from this original. So you need the two things. You need f of x, which is the original random variable. You need this mapping between f of x and between x and this new random variable, and these two together should be able to make you characterize this new random variable, right? Another example I gave is if the price of oil is a random variable, then the price of petrol might be a function that depends on this. So if I gave you the price of oil and I gave you that mapping, wouldn't you be interested in defining this new random variable? Now the function of a random variable is another random variable, which we can obtain from the original PMF or PDF. Okay, we already saw how it can be very straightforward, right, in terms of getting the expected value. Now getting the expected value of this new random variable can be fairly straightforward. We already saw that suppose y is equal to g of x. This is the transformation between x to this new quantity called y. Independently, x is a random variable that is characterized by small f of x, right? But if you had y is equal to g of x, getting the expected value of y, and I'm dealing only with continuous, you can apply this to discrete as well, can be very straightforward. Again, the minus infinity to infinity are placeholders, right? It's basically from going from the lowest to the highest possible value. Now, many a time, you're not just happy characterizing the expected value. You want to characterize the probability density function of y. Okay? I want to know what is my random variable called revenue that I make daily. What do I have in my hand? The random variable of number of people who walk into my store. How the number of people who walk into my store and how that translates to profit is some mathematical function. How do I take these two and define the random variable called number of people, my revenue? Okay? We primarily deal with the cumulative distribution function in order to do this. Okay? So what you have is small f of x, right? So you'll have small f of x. With small f of x, you should be able to characterize capital F of x. Correct? Capital F of x is in which form? So it's in the form that probability that x is less than or equal to x is nothing but your capital F of x. Correct? Wait, does the erase work? No. Just give me a second. So this will be capital F of small x. We're all familiar with this, right? So how did we get capital F of x? From small f of x. Now, just as a refresher, if you remember, how did we go from small f of x to capital F of x? By integrating from minus infinity to that point. Obviously, in the discrete space, what would you be doing? You'll be summing. Now, obviously, if you were integrating to go from small f of x to capital F of x, how will you go from capital F of x to small f of x? You'll be differentiating. So that's fairly elementary. Okay, so we have this capital F of x. Now, what we want is capital F of y, because we know that if we can get capital F of y, we can differentiate it and get to small f of y. How can I go from capital F of x to capital F of y? Well, I start by saying capital F of y is technically nothing but probability of y getting a value less than or equal to small y, some number. Okay. Now, we have defined capital Y as some function of capital X. So you can rewrite this as g of capital X less than or equal to some value y. Right? So g of x, can be something like x square, e power x, something. Some transformation exists. Imagine my profit is a function of the square of the number of people who walk into my store. It doesn't make sense, but you get the gist, right? So you can say, what is the probability that this function of x will be less than or equal to y? Now remember, always whenever you see a small x or a small y, in your head, you should just be making a translation to a number, right? Just remember, capital X and capital Y are random variables that capture a phenomena. Small x and small y are actual variates. So you're literally asking, what is the probability that this function of x will be less than or equal to 34, 29, 7.3. So small y is nothing but a number. But what you can do now, given that g of x should be less than y, is you can do some amount of basic algebra and reshuffle such that you're capturing the probability that x is less than or equal to g inverse of y. Right? In other words, if you're asking a question like, what is the, so g of x is, let's say, x square. You're saying what is the probability that x square is less than or equal to 3? Essentially, y is some number 3, right? So if you're asking what is the probability x square is less than or equal to 3, what should x be less than or equal to for x square to be less than or equal to 3? You'll have to take square root on the other side, right? That's what I mean by taking the g inverse. So you're asking questions like, what is the probability e power x is less than or equal to 25? But for e power x to be less than or equal to 25, what is, you can rewrite that as probability that x will be less than or equal to something, ln of 25, right? So this is what I mean by g inverse, the inverse of the function that was being mapped. Now, the beauty of this is, what is this functional form? Nothing but this, right? Probability that capital X was less than or equal to some value. G inverse of y is just some transformation on some real number, right? So all you'll have to do is go to capital F of x and substitute g inverse of y into that, right? And that will essentially give you capital F of y. Once you have capital F of y, you can just differentiate it and you'll get small f of y. We'll definitely do a tutorial problem where we take a concrete example like this and go from one distribution to the next. But this is a very powerful tool, which is to be able to start with a particular density function, look at mappings of it, and move to other density, to define new random variables through this process. Okay? Okay. The next topic that I want to briefly touch upon is on multiple continuous random variables. Of course, it applies to discrete as well, but typically when you cover it for continuous, the discrete part is more elementary or obvious. We'll start with a simple case where you have two continuous random variables. Now, why do you want to define a continuous, why do you want to define a multiple continuous random variable? Why can't you just keep them separate? What if they're dependent on each other? What if they co-affect each other's values? Keeping them separate might not help you answer certain important questions. So suppose I just define two completely independent variables. Let us say the mileage I get in a vehicle and the number of people sitting in the vehicle. These are two random variables, right? Now, these two might be dependent on each other. Maybe certain values of mileage can only be experienced, certain very bad values of mileage, when many people are sitting in the vehicle, right? But if I blindly ignore that, I will have some density function. I will have some density function for mileage, and I'll have some density function for number of people sitting in the vehicle, and that will completely ignore which combinations are really possible and not. So we need to have some way of referencing f of x comma y together to know the likelihood of combinations existing. Now, it's very easy to think in the discrete space when you have discrete number of people and discrete possible, if you had discrete buckets of mileage. But in the continuous space, the same thing applies. I need to know the relative likelihood of various combinations coming to B. Okay? So for that purpose, we want to define a f of x comma y. All right, and then what is it supposed to mean? It's supposed to really mean just the same way as you're supposed to understand continuous random variables. It's supposed to characterize the. Just let me erase this. It's supposed to characterize the likelihood that a random variable can take on specific values between, let's say, x can take on values between a and b, and y can take on values between c and d. So again, if you get an f of x comma y, right? That's a function which has an x and a y in it. If you go plug in a particular value of x and a particular value of y, you're going to get some number. Is that the probability of getting that x and that y? No. Just the same way as in the continuous space, the probability of a particular point, whether it's a 2D plot or a 3D mountain, does not matter. It's still 0. But I can define some area on the base of the mountain and that volume under the curve. Right now it's volume under the curve because you have two axes, x and y. Right? So in the past, you had something that looked like this, x, and this was f of x. Right? Now you might have something that's a little more 3D. You have x, and this is y, and this f of xy is like this kind of mountain, and I'm not very good at drawing this, but you get the picture. It's like this 3D mountain that exists on the xy, with sitting on top of the xy plane, and its height is coming on the third dimension. And what you're characterizing, so the volume under the curve now needs to be 1, right? And you can take any sliver of this volume, and that will give you within that range what the probabilities are. That's what the PDF is supposed to mean. So the probability that x takes on a value between a and b and y simultaneously takes on a value between c and d, this is that simultaneously is important, is characterized by this integral. So instead of a single integral now, you have a double integral where you're integrating over x for a through b and y from c through d. Okay? Now, understandably, the sum of all probabilities or the total area under the curve should be equal to 1. The minus infinity and plus infinity are placeholders. Many continuous distributions do go out to infinity in all other directions. The others that don't need to be integrated from. Their density of any point less than the lowest possible value is 0 anyway. Okay. Two very useful concepts to cover here are marginals and conditionals. So let me just erase this a second. So we're going to define this thing called the marginal distribution, which basically means, look, you've defined this thing of x comma y, and it's this 3D thing that's sitting on top of a table. Okay? But more often than not, I sometimes just want to know what is the distribution of x. At which point you will turn around and say, see, in reality, you had a distribution, a probability distribution, probably not my best example, but we'll stick with it, which is mileage and number of people sitting in a car. And let's just say the problem is number of people sitting in a car is discrete, but let's say mileage and ambient temperature. Let us say ambient temperature plays a huge role in mileage, making a case for let's relating the two, and both of these are continuous random variables, right? So different mileages and different temperatures. Okay, now you've defined this 3D bivariate random variable. Sometimes you might just want to know what is the density function, the PDF of mileage. At which point someone will turn around and say, for what temperature? Because you've defined these two together. Now at any one temperature, now again I want you, this is more of a visualization exercise and I'm kind of constrained by my ability to draw very well. Think of this tabletop, okay, as the base. So one edge of it is x, the other of it is y, and you have this fancy mountain coming out of it, right? If you look to me and say, I'm only interested in knowing about one of these axes, which is mileage, I don't care about temperature, I'll still have to turn around and say, given the mountain you have defined, I can give you the distribution for mileage in one of two ways. The first way is, tell me a given temperature. For a given temperature, which could be the short or the breadth edge of this table, I can fix a value, and I can take a slice of the mountain, and the image that I get from that slice would be the random variable, which will tell me about. Now, those are called conditionals. Okay, for a given value of y, and I don't even have to define the y. I can just say, I will substitute y later. You remember f of x comma y was in terms of x's and y's? Now f of x given y will still be in the form of x's and y's with the understanding that y is nothing but a parameter, a number that you're going to substitute in there. And the second you substitute that number, you'll have a random variable composed of only x. And that random variable composed of x will tell you what is the distribution of mileage when temperature is 24, when temperature is 23. So this is an important point, because think about it, f of x given y, the conditional distribution, is also going to have x elements and y elements in it, just like f of x comma y did. But what it's supposed to mean is that y is nothing from our perspective but nothing but a parameter. You substitute any value and immediately you get a distribution. You can't do that with f of x comma y, because substituting a value of y was a meaningless thing, remember? Okay. The other thing you can do is you can say, look, I don't want to give you a value of y. Why should I come and tell you that y is okay? Then what y should I assume? Well, assume y in accordance to its distribution. Right? So there are two ways. You're asking me for the random variable that defines mileage. Mileage, just mileage itself can be described as a random variable. No problem. Okay. Now for what? Ambient temperature. Because for different ambient temperatures, the distribution called mileage looks a little different, which is why we modeled it as a joint PDF in the first place. Now you come to me and say, one way to solve this problem is I will tell you what y is. You substitute for different values of y, you give me different random variables called mileage, we'll work with that. Those are called conditional distributions. The other way of defining it is to say, well, imagine if you were going to experience y, which is ambient temperature, in accordance to its likelihood. Maybe 230 degrees is not really possible, so don't give any weightage to that. But imagine you weighted y in accordance to its likelihood, and therefore substituted different values of y, and therefore aggregated all the different f of x's that you got as a result of it. Those are called marginals. One way of thinking of marginals is if you have this 3D table. So we spoke about conditionals as if you have this table with a mountain on top of it. Taking slivers on any one axis is like giving you the conditional distribution of one of the variables with respect to the other variable. A marginal can be in some way thought of as this kind of shadow that you project onto either of the screens on either side. It's not technically a shadow because shadows don't go through, but imagine you had a way of taking that mountain and pushing it against the wall and experiencing a particular density onto a surface. That's really what you're doing with respect to marginals. You're basically taking any one of the variables and saying, I'm going to assume that variable happens in the frequency of its density function. Now can you tell me what the probability density function of the other variable is? So if we were interested in f of x, the marginal of f of x, then what we would really be doing is integrating f of x comma y through all the possible values of y. So with respect to dy, you take f of x comma y and you integrate it. This is still going to result, because you're integrating it with respect to dy, all the y terms will get substituted with the minus infinity and infinity. You will still have a function that is a function of x. That function of x is your f of x, is your random variable x in this joint space. Now, the conditional, as I described to you, is capturing the density function of x for a specific value y is equal to y. And again, you can think of it from your probabilities, conditional probability that we spoke about an hour back. And what you're really trying to characterize is, so what you're trying to do is you're trying to characterize f of x comma y and divide it by f of y, right? So in other words, think of it this way. What you're trying to do is you're trying to renormalize for a subset of the event space. So you have a particular distribution, and you're trying to scale it up or scale it down with respect to f of y. So you're saying f of y has happened. Given that f of y has happened and that y value is equal to a specific value, how does my new distribution f of x actually look like? Okay. If you go back to your, again, in terms of your intuition, if you go back to this idea that P of A given B, which you understood more in terms of single events, was nothing but P of A and B. divided by P of B. That's really what you're trying to do in functional form. Okay. Okay. I think I'll stop there. I think we've also run out of time. Just so that all of this does not seem entirely theoretical mumbo jumbo, I just wanted to give you some popular distributions and how typical functions actually look like, right? We probably won't have time to go into each of them, but we've definitely covered the general principles. So what we called as an f of x, now you're going to actually go and take a particular value for a particular distribution, substitute it, and hopefully that will get strengthened during your tutorials. We'll conclude with that. Okay, thanks.